Earth was once a world no human could survive. Its days were shorter, the moon loomed larger, black oceans carried toxic sulfur, and the continents lay bare beneath a sky with almost no breathable oxygen. Yet inside that hostile planet, something extraordinary was already unfolding. Microbes were reshaping the atmosphere. Ancient continents were colliding into Rodinia, and hidden freshwater lakes were giving complex cells a place to experiment with the first steps toward multicellular life. For those who enjoy calm journeys through deep time, a like helps this story reach more curious minds, while subscribing and sharing keeps future scientific explorations moving forward. Thank you sincerely for spending part of the day, or perhaps part of the night, with this ancient world. What time is it where this story finds its listeners, and where in the world are they watching from? A comment would be warmly welcomed. Now, the journey can begin, back to the Earth of billions of years ago. Earth begins not as a blue world, nor as a green one, but as a sphere of heat moving through darkness. Around 4.5 billion years ago, the young sun is already shining, yet the space around it remains crowded with dust, rock, metal, and fragments left over from the birth of the solar system. Gravity draws these pieces together. Small bodies become larger bodies, and larger bodies collide with still greater force. The growing Earth gathers mass through a long sequence of impacts, each one releasing heat, melting rock, and reshaping the surface before any landscape can endure. There are no oceans, no continents, no quiet valleys, and no stable sky. The planet is a restless body under construction, its outer layers repeatedly broken and remade. Much of its heat comes from collision, but not all of it. Dense metals sink toward the center, releasing more energy as they move inward, while lighter minerals rise above them. Radioactive elements also decay within the young planet, adding their own slow warmth. As iron gathers at the center, the young planet begins developing the layered structure that still defines it. A metallic core forms beneath a vast mantle of hot silicate rock. Motion within the electrically conducting outer core may already be generating a magnetic field, though the strength and steadiness of that early shield remain difficult to reconstruct. Such a field matters because the young sun is active, sending streams of charged particles across the inner solar system. The atmosphere is thick, and gravity holds it close, but the space environment continually tests its stability. Earth is therefore shaped from both directions, heated from within and exposed from above. The deep interior drives melting and volcanism, while radiation and impacts disturb the surface. Between them lies a thin, cooling shell, fragile in scale yet increasingly important. Every patch of crust that survives creates another chance for minerals to separate, water to collect, and chemical complexity to persist beyond a single eruption or collision. Together, these processes create a world that is largely molten, with a deep ocean of magma glowing beneath a thick atmosphere of vaporized rock and volcanic gas. The surface does not resemble the familiar ground of later ages. It is fluid, unstable, and bright enough in places to shine through the darkness like heated metal. Above it hangs an atmosphere without breathable oxygen. It contains steam, carbon dioxide, nitrogen, sulfur compounds, and other gases released from the interior. Clouds may form, but rain falling into the heat would vanish again before it could remain. The Earth is not yet a place where water can gather calmly. It is a place where water cycles between vapor, cloud, and steam, waiting for the planet to lose enough heat. The young Earth also turns more quickly than it does in the modern age. A day is far shorter, and the sky changes at a pace that would later seem unnatural. Yet even this rapid rhythm is not permanent. A vast collision soon changes the planet more deeply than almost any event that follows. A body roughly the size of Mars strikes the young Earth at an angle, tearing material from the outer layers and hurling it into orbit. The impact is so energetic that large regions of the planet melt again. Rock vapor fills space around the wounded world. From the orbiting debris, gravity begins another act of assembly. The fragments collide, combine, and gradually form the Moon. At first, the Moon hangs much closer to Earth than it does in later time. It appears enormous in the sky, and its pull raises tides of extraordinary strength in whatever molten or liquid layers can respond. The Earth and Moon begin a long exchange of motion. The planet's rotation slowly loses energy, while the Moon drifts outward. This process continues for billions of years, but in the beginning its effects are especially powerful. The young world is not merely cooling. It is being shaped by a companion born from catastrophe. After the Great Impact, the surface remains dominated by magma. Heavy minerals sink, lighter minerals crystallize above them, and the first crude crust begins to appear. It does not last. Asteroids and planetary fragments still move through the inner solar system, and collisions remain common. Each large impact can puncture the crust, open new seas of molten rock, and release fresh clouds of gas. The surface becomes a patchwork of temporary skins, broken before they can mature. Yet beneath this violence, change is moving in a steady direction. Space is cold, and the Earth radiates heat away. The outer layers begin to thicken. Crystals form. Dark volcanic rock spreads across broad regions. The planet remains hostile, but hostility itself is becoming more organized. Instead of a single global magma ocean, there are solid surfaces interrupted by lava, eruptions, and impact scars. Some of the oldest surviving minerals on Earth preserve hints of this transition. Tiny zircon crystals, formed in ancient magmas and later trapped inside younger rocks, suggest that portions of the crust cooled surprisingly early. Their chemistry also points toward interaction with liquid water at a time when the planet is still young. These crystals do not preserve complete landscapes. They are fragments of evidence, carried through immense stretches of geological change. Yet they imply that the first stable surfaces may appear earlier than once expected, and that water may begin collecting while the solar system is still violent. The source of that water is not a single event. Some arrives within the materials that build Earth. Some is released from minerals as the interior heats and differentiates. Some may also be delivered by water-rich asteroids. However it arrives, the water remains trapped for a time in the hot atmosphere. As the surface cools, steam condenses, clouds thicken. Rain begins to fall in a world without soil, plants, or rivers. At first the rain strikes hot rock and rises again as vapor. Later it survives for longer. Storms may continue for ages, filling low regions, dissolving minerals, and carrying them into the first basins. The earliest oceans take shape beneath a dimmer young sun. Though the atmosphere is rich in greenhouse gases that help hold warmth near the surface, these oceans are not blue in the modern sense. Their colour depends on suspended minerals, dissolved iron, volcanic ash, and the changing light beneath a dense sky. The shorelines shift constantly as the crust moves and volcanic plateaus rise. There are no rooted continents in the modern form, only fragments of crust that merge, break, sink, and return. Even so, the existence of persistent liquid water marks a profound change. Heat is no longer the only force governing the surface. Water begins to weather rock, carry sediment, and create chemical pathways that did not exist in the magma ocean. The atmosphere also begins to evolve. Carbon dioxide dissolves into rain and ocean water. It reacts with minerals in the crust, forming compounds that may later be buried. Volcanic gases continue to replenish the air, but the planet now contains active cycles linking rock, water, and sky. These cycles are still unstable, and the young sun is less luminous than it becomes in later ages. The balance between freezing and boiling is delicate, yet the Earth remains within the narrow range where oceans can endure. This persistence is one of the great quiet mysteries of early planetary history. The conditions are violent, the atmosphere is unbreathable, and impacts continue, but liquid water survives often enough to reshape the surface and prepare new environments. Deep below the oceans, heat from the interior drives hydrothermal systems. Water seeps into cracks, warms near magma, reacts with rock, and returns carrying dissolved chemicals. Along the seafloor, mineral-rich fluids create steep gradients in temperature and chemistry. These gradients provide energy. Long before sunlight supports complex ecosystems, the planet already contains places where chemical reactions can organize matter in new ways. Whether life begins in such settings, in shallow pools, along volcanic shores, or through several environments working together remains uncertain. The first chapter does not yet reveal the answer. It only establishes the stage. Earth is no longer entirely molten, yet it is still far from calm. Its crust is thin and mobile. Its atmosphere is dense and alien. Its oceans are young, hot, and chemically active. The moon looms near. Tides move with exceptional force, and the sky may still flare with incoming debris. No familiar landscape exists, but the essential parts of a living planet are beginning to gather: rock, water, atmosphere, and energy now interact across a surface that can endure long enough to preserve change. From the silence of these first oceans, the next transformation waits without form or name. The moon begins close enough to dominate the young sky. It is not yet the distant pale disk of later ages, but a vast bright presence suspended above a world still settling from its own creation. From Earth, it appears much larger than it will in the future, crossing the sky with a speed that reflects the planet's faster rotation and the moon's tighter orbit. The relationship between the two worlds is energetic from the beginning. Earth turns rapidly, the moon circles nearby, and gravity transfers motion between them in a slow exchange that never stops. Each tide raised in rock, magma, and water carries a small amount of rotational energy away from Earth. The planet's spin gradually slows, while the moon moves outward. This change is almost invisible from one lifetime to the next, but across deep time it reshapes the length of every day and the spacing of every month. In the earliest era, the effect is much stronger because the moon is much closer. Its pull rises steeply with proximity, and the tides it creates are enormous compared with those of the modern world. Before stable oceans fully cover the surface, the tides flex the hot crust and stir the remaining molten layers. Solid rock itself responds, lifting and falling under the moon's gravity. These movements are subtle compared with an eruption or impact, yet they repeat with relentless regularity. The young Earth is kneaded by its companion. Heat produced by tidal friction adds to the planet's interior warmth, while repeated deformation opens cracks and influences the movement of magma. The moon does not control the planet's geology, but it becomes one of several forces that keep the early surface active. As liquid water gathers, the tides become even more visible. Shallow seas surge across raw volcanic plains, then retreat, leaving broad surfaces exposed to air and sunlight before flooding them again. Coastlines may shift by great distances over a single cycle, because many early basins are shallow and irregular. The sea does not rise and fall against stable continents. It advances over fractured crust, around volcanic islands, through impact basins, and across low regions that may disappear beneath lava in a later age. Every tide rearranges sediment, mixes water, and moves dissolved minerals from one environment to another. in places where water collects in sheltered pools, evaporation concentrates salts and organic compounds. When the tide returns, those pools are refreshed, diluted, and disturbed. Such cycles may later prove useful to prebiotic chemistry, though no single setting can be identified as the birthplace of a life. The importance of the tides lies less in any one location than in the endless repetition they create. Wetting and drying, heating and cooling, mixing and separating occur again and again across the margins of the first oceans. The young moon also helps steady the orientation of Earth's axis. The planet does not spin perfectly upright, its axis is tilted, and gravitational interactions can alter that tilt over long periods. A large nearby moon resists some of the most chaotic variations that might otherwise occur. The effect is not absolute, and the young solar system remains a place of disturbances, but Earth and Moon already behave as a coupled system. Their shared motion influences the rhythm of light, temperature, and tides across the surface. This does not make the planet gentle. The atmosphere remains thick with volcanic gases. The sun is active. Impacts continue. Yet amid this disorder, regular cycles are becoming established. Day follows night more quickly than in the modern world. The exact length of an early day changes with time and is difficult to reconstruct for the oldest eras, but it is certainly shorter. The sun rises, crosses the sky, and sets with unfamiliar speed. Winds respond to rapid rotation, and weather systems are shaped by a stronger rotational influence. The oceans, once they become widespread, feel both the fast turning of the planet and the pull of the nearby moon. Currents form under conditions unlike those of later Earth. Tidal waves travel through basins that change as crust is created and destroyed. Where the seafloor narrows or slopes upward, the water piles higher. Where channels focus the flow, currents become violent enough to scour rock and carry large fragments. Elsewhere, in deeper basins, the tides become broad internal movements hidden beneath the surface. Water layers slide over one another, mixing heat and chemistry through the young seas. This stirring may help prevent some regions from becoming permanently stagnant. It also moves material between the sunlit surface and the dark water below. The moon therefore shapes not only the visible edge of the ocean, but also the hidden circulation within it, above the tides. The moon's appearance changes through phases that pass more quickly than they do later. A month is shorter because the moon is closer and completes its orbit in less time. The repeated brightening and fading of the lunar disk adds another rhythm to the planet, though no eyes exist to witness it. During a full moon, the night surface is washed with stronger light than future landscapes receive. During a solar eclipse, the young moon appears larger than the sun and can cover the solar disk completely. These events have no observers, but they reveal the geometry of a system still evolving. The moon is not fixed in place. Every tide raised on Earth pulls slightly ahead of the moon because Earth rotates faster than the moon orbits. The gravitational attraction of that displaced bulge tugs the moon forward, giving it energy and pushing it into a wider orbit. At the same time, the moon pulls backward on the bulge, slowing Earth's spin. The process is gradual, but its direction is clear. The days lengthen, the months lengthen. The moon shrinks slowly in the sky as the distance grows. Some of the transferred energy becomes heat through friction in the oceans and solid Earth. While some enters the moon's orbit, this exchange continues through every later age. Even when continents form, life spreads, and animals eventually track lunar cycles. In the beginning, however, the mechanism operates on a world without beaches in the familiar sense, without coral reefs, and without forests leaning toward moonlight. The tides move through darkness over bare stone. Their force works on minerals, sediments, and water alone. The young moon may also influence volcanic activity indirectly by stressing faults and magma chambers. The effect is modest compared with the immense heat already rising from Earth's interior, yet on a planet close to thresholds, even small repeated stresses can matter locally. Cracks open and seal. Molten rock moves through zones of weakness. Water enters fractured crust, becomes heated, and reacts with minerals before returning to the ocean. Each tidal cycle adds another slight movement to a system already in motion. Over time, these repeated disturbances help create a surface of constant exchange. The boundary between ocean and land never stays still. The boundary between crust and water is chemically active. The boundary between Earth and space is guarded only partly by atmosphere and magnetic field. The moon hangs above these boundaries as both consequence and cause, born from destruction and now helping organize the world that survived it. It also preserves evidence that Earth later loses. Without oceans, weather, or plate tectonics, the moon keeps ancient scars while Earth's surface is repeatedly melted, buried, folded, and recycled. Its battered face becomes a record of the violent environment both worlds endure. Yet the moon itself is changing. It cools faster because it is smaller. Its early magnetic activity weakens, its volcanism declines, and dark basalt plains begin forming in regions fractured by ancient impacts. From Earth, those changes slowly create the contrast of bright highlands and dark plains, though the familiar pattern takes a long time to emerge. Meanwhile, the Earth beneath it grows less incandescent, stable water becomes more common, sections of crust survive for longer. The atmosphere loses some of its most extreme heat. The moon remains enormous, but its role is changing from participant in a shared catastrophe to regulator of repeating cycles. The planet is still dangerous, but it is no longer formless. Its days, tides, and months now follow patterns that can persist. Those patterns do not guarantee life, yet they create continuity, and continuity allows chemistry to build upon earlier chemistry, rather than begin again after every disturbance. In this way, the moon's greatest influence may be found not in a single dramatic event, but in repetition. It raises water, flexes stone, slows the planet, steadies its orientation, and marks time across an empty world. Each cycle is nearly the same, yet never identical. The moon moves a little farther away. The day grows a little longer. The tides lose a fraction of their former strength. Beneath that slow celestial change, Earth continues cooling toward a state in which oceans can remain, crust can endure, and the first hidden steps toward life can take place. The first enduring oceans gather beneath a sky that would appear almost unrecognizable. There is no clear blue arch, no breathable air, and no familiar balance of gases. The atmosphere is thick with carbon dioxide, nitrogen, steam, sulfur compounds, methane, and traces of other volcanic products released from the planet's interior. Clouds spread across much of the sky, fed by water vapor rising from hot seas and freshly cooled rock. The sun is fainter than it becomes in later ages, yet the surface remains warm because greenhouse gases trap heat near the ground. This balance is delicate. Too much heat would keep the water in the air, while too little would allow ice to spread across the planet. Instead, Earth remains within a narrow middle state where liquid water can persist, evaporate, condense, and fall again. Rain becomes one of the first great sculptors of the surface. It strikes volcanic plains, gathers in impact basins, and runs across dark rock that has never known soil. Streams appear wherever the land slopes, though their paths are temporary because eruptions, impacts, and crustal movement repeatedly erase them. Water enters cracks, dissolves minerals, and carries them toward the seas. The first rivers do not cross forests or grasslands. They move through silent landscapes of basalt, ash, glassy lava, and broken stone. Their channels are bare and unstable, yet they begin the long work of connecting atmosphere, land, and ocean. Every drop that reacts with rock changes both materials slightly. Carbon dioxide from the air enters rainwater and forms a weak acid. That water attacks exposed minerals, releasing calcium, magnesium, iron, and other elements. Some of the carbon becomes locked into new compounds that wash toward the ocean and later settle into sediment. This process slowly removes carbon dioxide from the atmosphere, while volcanoes continue adding it back. A planetary cycle begins, regulated not by life but by chemistry, rainfall, erosion, and heat rising from below. The young oceans are chemically rich. Iron dissolved from the crust enters the water in great quantities because little free oxygen exists to force it out. Hydrothermal vents add metals, sulfur, hydrogen, and heat from the seafloor. Volcanic islands release ash and gases into the waves. Meteorites contribute additional material from space. The seas become a vast mixture of dissolved elements, suspended particles, and simple molecules moving through changing temperatures and pressures. Their colour is uncertain and likely varies from place to place. In some regions, dissolved iron may give the water a greenish cast. Near volcanic centres, ash can darken the surface. Shallow basins may become cloudy with mineral sediment, while deeper water lies almost black beneath the weak light. No single image captures the whole world, because the oceans are restless and the crust beneath them is still developing. Heat escapes through countless fractures. New seafloor forms where magma rises and cools. Older crust sinks or is altered by water. The modern pattern of plate tectonics may not yet operate in the same steady way, but the planet's outer shell is already mobile enough to recycle material and create strong differences between regions. In some places, broad volcanic plateaus rise above the sea. Elsewhere, thin crust founders and disappears into hotter depths. Small pieces of buoyant crust survive longer, gradually changing in composition as repeated melting removes dense minerals and leaves lighter rock behind. These fragments become the beginnings of more enduring continental material. They are not yet the wide, stable continents of later Earth, but they provide islands of persistence in a world of renewal. Around them, shallow seas form. Sunlight reaches the bottom where the water is clear enough, warming pools and tidal flats. The nearby moon still raises powerful tides, repeatedly flooding and exposing the edges of these primitive lands. Each cycle concentrates some substances and disperses others. Water evaporates from sheltered basins, leaving salts and minerals behind. Rain and tides return, dissolving them again. Lightning, ultraviolet radiation, volcanic heat, and chemical energy act on gases and molecules across the surface. None of these forces guarantees the appearance of life, but together they create an immense range of environments in which matter can react. The sky itself remains active and dangerous. Without a protective ozone layer, ultraviolet radiation reaches the surface far more strongly than it does in later eras. The upper atmosphere is also exposed to the young sun's energetic emissions. Charged particles strike gases, break molecules apart, and drive chemical reactions. Some lighter atoms escape into space. Hydrogen is especially vulnerable, drifting upward and being carried away more easily than heavier gases. Earth therefore changes not only through what volcanoes release and oceans absorb, but also through what the planet loses. The magnetic field, if already established, offers some protection by deflecting part of the solar wind. Yet it does not create a gentle environment. The atmosphere remains turbulent, and storms draw energy from warm water and rapid rotation. Clouds build over the seas, winds sweep across open water, and rain may fall with extraordinary intensity. In places, lightning flashes through volcanic haze. The thunder passes over oceans with no animals to hear it. Beneath the storms, the seas absorb heat and carry it around the planet. Currents move warm water toward cooler regions and return colder water toward the tropics. The details differ from modern circulation because there are no large familiar continents guiding the flow, and the day is shorter. Even so, the ocean already acts as a planetary reservoir, storing heat and reducing extreme swings in temperature. Its depth protects water from immediate evaporation, while its chemistry buffers changes in the air. The ocean becomes part of the mechanism that keeps the surface habitable. Deep below, pressure rises and sunlight disappears. Water enters fractured rock, warms near magma, and emerges through hydrothermal systems. Some vents release dark, mineral-rich fluids into the ocean, where sudden cooling causes particles to form and settle. Others produce gentler alkaline flows through porous stone. Across these environments, strong chemical gradients exist between hot and cold, acidic and alkaline, oxidized and reduced materials. Such gradients can drive reactions without sunlight. Molecules form, break apart, and recombine along mineral surfaces. Tiny pores in rock provide sheltered spaces where compounds can become concentrated instead of drifting away into the open sea. The exact pathway from chemistry to biology remains unresolved, and the oldest rocks preserve only fragments of evidence. Yet the young Earth now contains many of the conditions later life repeatedly uses: liquid water, carbon, minerals, energy, and surfaces where reactions can persist. The oceans also shield their depths from ultraviolet radiation, creating places where fragile compounds can survive longer. Near the surface, sunlight provides energy but also damage. Far below, darkness protects molecules but limits certain reactions. Between these extremes lies a shifting range of habitats, from tidal pools to warm seafloor cracks. The origin of life may depend on exchanges between several such settings rather than a single isolated cradle. Materials produced in the atmosphere can fall with rain. Compounds formed near vents can move through currents. Minerals weathered from land can collect in shallow basins. The entire planet participates in the chemistry. Over time, the sky begins to lose some of its steam as more water settles into the oceans. Carbon dioxide also changes as weathering and burial compete with volcanism. Methane may accumulate when chemical reactions or early microbes begin producing it, though its abundance remains uncertain. The sun continues brightening slowly, while the atmosphere and oceans adjust in response. Earth avoids permanent boiling and permanent freezing through a balance that is never fixed. Volcanoes, rainfall, rock alteration, ocean circulation, and atmospheric escape continually shift that balance. Stability emerges not from stillness but from movement. The planet remains violent on human scales, yet across geological time it begins to preserve continuity. Oceans endure between impacts. Basins survive long enough to collect sediment. Crust remains exposed long enough to weather. Chemical products persist long enough to become ingredients for further reactions. Under the dark clouds and the fainter sun, the surface no longer resets completely after every disturbance. The world has acquired memory. Layers of sediment record floods, eruptions, and changes in water chemistry. Minerals carry traces of temperature and interaction with liquid water, even when later tectonic activity destroys most of these ancient records. A few fragments remain, suggesting that the early ocean arrives not as a brief episode but as a lasting planetary presence. Beneath an alien sky, Earth has crossed another threshold. It is still airless in the sense that no animal could breathe, still barren in the sense that no plant covers the land, and still dangerous in almost every visible way. Yet water now links the deepest rock to the highest cloud. It circulates through crust, ocean, and atmosphere, carrying heat and chemistry between them. The planet is becoming not merely cooler, but connected. In that connected world, the first true living systems can begin to emerge from processes that are no longer isolated and fleeting. Beneath the young oceans, Earth's outer shell begins to behave less like a single cooling skin and more like a mosaic in motion. Heat still rises from the interior, but it no longer escapes only through random fractures and vast fields of lava. In many regions, the crust starts to organize into separate pieces that spread, collide, bend, and sink. The exact beginning of plate tectonics remains uncertain because the oldest evidence has been altered, yet the planet clearly develops a lasting habit of recycling its surface. New crust forms where hot material rises. Older crust cools, thickens, and becomes dense enough to descend. Between these zones, pieces of buoyant rock resist destruction and survive. From this movement, the first durable continents begin to take shape. They are smaller and more fragmented than later continents, often surrounded by shallow seas and volcanic arcs. Their surfaces are barren, dark, and exposed to weather without roots or soil. Even so, they mark a decisive change. For the first time, significant portions of the surface can remain above water for long stretches, preserving minerals, sediments, and chemical records that the ocean floor continually loses. The oldest continental cores form from repeated episodes of melting and separation. Basaltic crust, rich in iron and magnesium, is carried downward or heated from below. Partial melting removes lighter material, creating magmas richer in silica. These magmas rise and cool into paler rocks that are less dense than the surrounding crust. Because they float higher on the mantle, they resist being dragged back into the deep. One generation of rock is built upon another. Volcanic islands merge. Fragments collide. Mountain belts rise where crust is compressed, then erode beneath rain and wind. The debris washes into nearby basins, where it becomes sediment and later stone. Through this slow cycle, the first cratons appear. A craton is an ancient stable heart of continental crust, thick enough and cool enough to endure while younger terrains gather around it. Some modern continents still contain these early cores, though they have travelled, collided, and been reshaped many times. Their survival reveals that Earth's surface is becoming capable of memory on a larger scale. A patch of crust can now persist for billions of years. The motion beneath it remains powerful. Hot mantle material rises, spreads sideways, and cools. Dense slabs descend into the interior, carrying water and altered minerals with them. At depth, these materials release fluids that lower the melting temperature of surrounding rock. New magma forms and rises toward the surface, feeding chains of volcanoes. Where two pieces of crust converge, one may sink beneath the other in a process called subduction. Where they move apart, new crust emerges between them. Where they slide past, faults store and release stress. These patterns may be irregular at first, while the hotter young mantle produces faster recycling and widespread melting. Still, the essential behavior is recognizable. The planet's skin is no longer fixed, it is circulating. Water plays a quiet but important role in this transformation. It enters cracks in the seafloor, reacts with minerals, and becomes locked into altered rock. When that rock descends, the water travels with it into the mantle. There it helps generate magma, which returns gases and new material to the surface. This deep water cycle links oceans to volcanoes and atmosphere to interior. It also weakens rock, making it easier for rigid plates to bend and move. Without liquid water, Earth's tectonic style might have developed differently or not persisted at all. The ocean therefore shapes continents not only by eroding their surfaces, but also by helping drive the processes that create and recycle them. Above sea level, the new land changes the atmosphere. Rain falls on exposed rock and reacts with fresh minerals. Carbon dioxide dissolves into water, enters chemical reactions, and becomes bound in sediments that may later be carried into the deep. As more continental surface appears, weathering becomes a stronger influence on climate. Volcanoes add carbon dioxide while weathering removes it. The balance between these processes acts over immense spans of time, helping prevent the planet from remaining permanently too hot or too cold. When volcanism increases, greenhouse gases can accumulate and warm the surface. When warm conditions bring more rainfall and faster weathering, carbon dioxide can be removed more quickly. This feedback is imperfect and sometimes overwhelmed, yet it gives Earth a mechanism for recovering from large changes. Continents also alter the oceans. Rivers carry phosphorus, iron, silica, and other nutrients from land into shallow seas. Before soil and plants, this transport is controlled by bare rock, rain, temperature, and volcanic activity. The nutrients arrive unevenly, creating coastal zones far richer than the open ocean. Shallow continental margins provide sunlight, mineral surfaces, and changing conditions. These environments may support growing communities of microorganisms, especially where tides and currents keep water moving. Life remains microscopic, but the geography of habitability is becoming more varied. Deep oceans, volcanic vents, island shores, tidal flats, and inland basins each offer different combinations of energy and chemistry. Plate movement continually creates new versions of these settings and destroys old ones. The earliest continents do not stay together. They drift across the globe, approach one another, and join into larger assemblies. Later they break apart again. This repeated joining and separation becomes the supercontinent cycle, one of the slowest rhythms in Earth history. A supercontinent forms when most continental blocks gather into one great mass. Heat then builds beneath the insulating crust, while rising mantle material stretches it from below. Rifts open, volcanism spreads, and the land eventually separates. New oceans form between the fragments, only to close in a later cycle. The details of the earlier supercontinents remain debated because so little rock survives. But ancient mineral grains and matching geological belts suggest that continental fragments are already participating in large-scale assemblies very early in the planet's history. Each collision creates mountains. Each mountain range begins to vanish almost as soon as it rises. Rain attacks exposed peaks, rivers cut valleys, and sediment moves toward the sea. Without vegetation to stabilize slopes, erosion can be rapid. The mountains may appear stark and dark, their surfaces striped with volcanic rock, pale intrusive stone, and rust-colored minerals. Yet their destruction is as important as their formation. Erosion exposes fresh rock to the atmosphere and delivers nutrients to the ocean. Sediment buries organic material and chemical compounds. Some of that buried matter escapes immediate recycling and becomes part of the crustal record. The moving continents therefore create both elevation and burial, both exposure and preservation. Earth's appearance changes with them. A world once dominated by water and volcanic islands begins to show more persistent land. The coastline grows longer and more complex. Archipelagos merge into larger regions. Shallow seas spread across low continental interiors when water levels rise, then retreat when uplift or cooling changes the balance. Under the fainter sun, clouds and greenhouse gases still control much of the climate. But geography now matters as well. Continents redirect ocean currents and winds. Mountain ranges force air upward, producing rain on one side and drier conditions on the other, even before plants, animals, or visible life. The surface develops regional climates. Some coasts are battered by storms. Some inland basins become salty under repeated evaporation. Some highlands may hold temporary snow or ice if elevation and latitude allow it. The planet is gaining variety, yet from a distance it remains alien. The land is bare. The sea may carry green, grey, or dark tones depending on chemistry and sediment. Volcanoes rise above the horizon and impacts still occur, though less often than before. The atmosphere remains poor in oxygen, and ultraviolet radiation reaches the ground. Nothing walks across the new continents. No roots split the rock, no forests darken the slopes. The only living presence is microbial, mostly confined to water, wet surfaces, and protected spaces. Still, the movement of the continents prepares conditions that later life will use. It creates shallow seas where sunlight reaches the bottom. It delivers nutrients from rock to water. It buries carbon and alters the atmosphere. It builds isolated basins where populations can follow separate evolutionary paths. Most importantly, it prevents the planet from settling into permanent uniformity. Every collision and rift rearranges the boundaries between ocean, land, air, and deep interior. The early continents are therefore more than inert ground. They are moving participants in a planetary system that is learning to regulate itself. Their rocks rise from melting, survive destruction, gather into larger masses and return fragments to the mantle. Across this endless circulation, Earth becomes increasingly different from worlds whose surfaces remain fixed beneath ancient scars. Its crust is always losing evidence. Yet that same destruction creates new environments. The continents never truly stand still, and because they move, the planet continues to change. Long before forests darken the land or animals stir the seafloor, life exists as a hidden presence in water. The planet has already spent immense ages cooling, cycling rock, and gathering oceans beneath an atmosphere almost empty of free oxygen. Across the surface, storms move over bare continents and volcanic islands, but the deepest transformation is taking place far below sight, in the dark ocean, where sunlight cannot penetrate. Heat and chemistry provide energy enough for living systems to endure. The earliest organisms leave only uncertain traces, because their bodies are soft, microscopic, and easily erased by later geological change. Yet the chemistry of ancient rocks suggests that life appears surprisingly early. Perhaps not long after liquid water becomes stable. Its first forms are simple cells without nuclei or complex internal structures. They are small, adaptable, and capable of drawing energy from reactions that do not depend on oxygen. In an ocean rich with iron, sulfur, carbon dioxide, hydrogen, and dissolved minerals, such cells find many possible ways to survive. Some use hydrogen released when water reacts with hot rock. Some depend on sulfur compounds carried from the mantle. Others may use methane, iron, or carbon molecules formed near volcanic systems. Their world is not illuminated by the sun, but it is far from empty. Along the sea floor, seawater enters cracks in the crust and descends toward hot rock. It warms, reacts with minerals, and returns through vents carrying a concentrated mixture of metals and gases. When the hot fluid meets cold seawater, dissolved material forms clouds of dark particles and builds mineral towers around the openings. These structures grow, collapse, and grow again, creating channels and pores where chemical gradients remain stable. On one side of a thin mineral wall, warm alkaline fluid may rise from the crust. On the other side, cooler ocean water carries different compounds. The contrast creates a natural source of energy. Modern cells maintain similar differences across their membranes, using them to power metabolism. This resemblance does not prove that life begins at vents, yet it makes such settings important in any reconstruction of the earliest biology. Mineral surfaces can gather molecules that would otherwise drift apart. Tiny chambers can concentrate carbon compounds, protect them from dilution, and allow repeated reactions to take place. Heat supplies energy, but the most useful environments may not be the hottest ones. Extreme temperatures destroy delicate molecules, while cooler margins around hydrothermal systems offer a balance between energy and stability. In these zones, chemistry can continue for long periods as water circulates through rock. The boundary between geology and biology becomes difficult to define. Reactions that begin without life may produce compounds later used by cells. Once a self-sustaining system develops, it can exploit the same gradients more efficiently, reproduce, and spread. The first living organisms do not transform the appearance of the planet at once. They remain invisible from above, confined to thin films, pores, sediment, and water. Their influence is chemical rather than visual. They take in gases and minerals, alter them, and release new products. They compete for energy, but they also change their surroundings in ways that create opportunities for other forms. One group may release methane that another can consume. One metabolism may produce sulfur compounds useful to a neighboring cell. In this way, communities form long before bodies, organs, or nervous systems exist. The ocean becomes an intricate network of exchange, built from organisms too small to see. The earlier cells must also solve the problem of boundaries. A living system needs to remain connected to its environment while keeping its internal chemistry distinct. Membranes provide this separation. They allow some molecules to pass and hold others back. Inside, genetic material stores information that can be copied, while proteins or simpler catalysts accelerate reactions. The exact sequence by which these parts arise remains unknown. Some models place self-copying molecules first, others emphasize metabolism within mineral compartments. Still others suggest that membranes, energy cycles, and genetic systems develop together through gradual cooperation. No ancient rock preserves the complete transition. By the time life leaves a recognizable chemical signature, many earlier stages have already vanished. The origin of life therefore remains less like a single moment than a long threshold crossed through countless experiments. Most fail. Some persist briefly. A few become capable of inheritance, variation, and natural selection. Once that occurs, evolution begins to preserve useful changes. Cells that gather energy more effectively leave more descendants. Membranes become better at controlling their contents. Molecular machinery becomes more reliable. Genetic information expands. The first biosphere may remain fragile, yet every generation gives it another chance to adapt. Deep ocean environments offer protection during this early period. Water shields cells from ultraviolet radiation and softens changes in temperature. The overlying ocean also provides stability when impacts strike the surface. A large collision can boil shallow water and darken the sky, but communities living in rock pores or deep sediments may survive. These hidden refuges allow life to endure through events that erase surface habitats. The young Earth remains violent, though the frequency of major impacts gradually declines. Each surviving population carries life across another disruption. Over time, cells spread beyond the vents and into a wider range of settings. Some live within ocean sediment, where organic compounds and minerals meet. Some colonize the surfaces of volcanic rock, others rise into shallower water, where sunlight offers a new and abundant source of energy. Before oxygen-producing photosynthesis appears, simpler forms of photosynthesis may already be using light without releasing oxygen. Such organisms draw electrons from hydrogen, sulfur compounds, or iron rather than from water. Their pigments may be purple, red, or green, allowing them to absorb particular wavelengths in the filtered light of microbial mats and shallow seas. These early photosynthetic communities expand the habitable world. Life is no longer tied only to chemical energy rising from the crust. It can capture energy falling from the sky. Along quiet shorelines and in shallow lagoons, layers of microbes begin forming mats over sediment. The upper layers receive light, while deeper layers use chemicals produced above or supplied from below. Each layer occupies a narrow chemical zone. The mat may be only a few millimeters thick, yet within it many metabolisms coexist. Sticky microbial films trap grains of sediment. New layers grow over old ones, building low rounded structures known as stromatolites. Some ancient rocks preserve these shapes, though similar forms can also arise through non-living processes. Where biological origin is secure, they reveal that microbial communities are already capable of changing the physical landscape. The structures rise slowly in sunlit water, layer by layer, recording tides, sediment, and growth. They are among the first visible signs that life is no longer merely surviving inside the planet, but beginning to shape its surface. Even so, the atmosphere remains hostile to modern organisms. Oxygen is still scarce, and many early cells would find oxygen poisonous. Their enzymes have evolved in a world where other chemicals carry energy. Methane released by microbes may become an important greenhouse gas, helping keep the surface warm beneath the faint young sun. Biological activity therefore begins influencing climate long before complex life appears. The connection works in both directions. Temperature controls ocean circulation and chemical reactions, while those reactions affect the gases entering the air. Life becomes part of Earth's planetary cycles almost as soon as it becomes widespread. The scale is still modest compared with the later ages, but the principle is established. Biology is no longer a passenger, it is becoming a geological force. The dark ocean remains the foundation of this transformation. Within it, simple cells diversify into branches whose deepest relationships are difficult to reconstruct. Some become ancestors of bacteria. Others belong to the lineage later called archaea, organisms often adapted to environments rich in heat, salt, acid, or unusual chemistry. Their names are modern, but their origins reach into a time when the planet itself is extreme. They exchange genes, adapt quickly, and occupy habitats that would defeat more complex cells. Through their activity, carbon moves between ocean and atmosphere, nitrogen changes into usable forms, and sulfur cycles through water and sediment. These invisible reactions prepare the conditions for every later ecosystem. Earth still appears empty from space. No green continents interrupt the bare rock. No large organisms cloud the water. Yet beneath the waves, life has crossed from possibility into persistence. It survives darkness, heat, pressure, and chemical scarcity. It learns to use the planet's restless geology as a source of energy, then reaches upward toward light. In doing so, it begins a process that will eventually alter the oceans, transform the atmosphere, and make the surface habitable for forms that cannot yet exist. The first living world is not bright or abundant. It is quiet, microscopic, and hidden in stone and water, but it endures, and endurance is enough to change the future. Oxygen begins as a dangerous waste product. In the shallow waters of the ancient Earth, certain microbes learn to capture sunlight with a new kind of chemistry, one that pulls electrons from water and releases oxygen into the surroundings. The innovation is simple in outline but revolutionary in consequence. Water is abundant, sunlight is reliable, and the process gives these organisms access to an almost limitless energy source. Yet the gas they produce is highly reactive. To many older forms of life, adapted to an oxygen-free world, it is toxic. The first oxygen does not immediately fill the atmosphere. It disappears into the planet almost as soon as it is made. Dissolved iron in the oceans reacts with it, forming solid iron oxides that settle onto the seafloor. Layer after layer accumulates, alternating with silica and other minerals, creating banded iron formations that survive in ancient rocks. Their striped appearance records a world in transition, a time when oxygen repeatedly enters the water and is consumed before it can spread. Volcanic gases also absorb the new gas. Reduced sulfur, hydrogen, methane, and minerals exposed on land all act as chemical sinks. The biosphere produces oxygen, but the planet has many ways to remove it. For a long interval, production and destruction remain closely balanced. Local pockets of oxygen may appear around microbial mats in sunlit shallows, while the wider ocean stays largely anoxic. Within these small zones, organisms encounter a chemistry unlike anything their ancestors have known. Some are poisoned, others retreat into deeper sediment, stagnant basins, or environments where oxygen cannot penetrate. A few evolve defenses. They develop enzymes that neutralize reactive oxygen compounds before those compounds damage proteins, membranes, and genetic material. What begins as protection eventually becomes opportunity. Oxygen can release far more energy from food than many older metabolic pathways. Cells able to tolerate it can use it to extract energy with remarkable efficiency. The same molecule that destroys one community becomes the foundation of another. This is not a sudden replacement of one world by the next. It is a long conflict between production, reaction, burial, and adaptation. The ancient oceans remain chemically divided. Surface waters may receive oxygen from photosynthetic microbes, while deeper waters continue to hold iron, sulfur, and gases formed without oxygen. Where these layers meet, sharp chemical boundaries develop. Microbes gather along them, each species occupying the narrow zone that suits its metabolism. Above, oxygen-producing cells draw energy from sunlight. Below, anaerobic organisms use sulfur, methane, or iron. Between them, other microbes consume the products of both. The ocean becomes a layered living system, structured by invisible gradients. Over time, the supply of easily oxidized iron in the upper ocean begins to decline. More organic carbon is buried before it can decay, preventing the oxygen used to create that material from being immediately consumed again. Tectonic change exposes fresh land and alters the flow of nutrients into the sea. The balance shifts. Oxygen starts to persist for longer in surface water and eventually enters the atmosphere in greater amounts. This rise, known as the Great Oxidation Event, unfolds more than 2 billion years ago. The name suggests a single dramatic moment, but the change is uneven, prolonged, and unstable. Oxygen levels climb, fall, and climb again. Different regions cross the threshold at different times. Even after the atmosphere changes, much of the deep ocean remains oxygen poor. Still, the direction of planetary history has altered. The atmosphere can no longer return easily to its earlier state because biology continues producing oxygen, and many of the largest chemical sinks have weakened. The consequences reach far beyond respiration. Methane, a powerful greenhouse gas, reacts with oxygen and becomes less abundant. The young sun is still dimmer than it will be in later ages, and the loss of methane may cool the planet sharply. Evidence in ancient rocks suggests that glaciers spread during this broad interval, perhaps reaching low latitudes. Ice covers regions that had once been warm, while the oceans beneath remain dark and chemically strange. The rise of oxygen therefore does not create an immediate paradise. It may help trigger severe climate stress, replacing one danger with another. Yet even glaciation becomes part of the transformation. Ice changes weathering, ocean circulation, and the movement of nutrients. When volcanic carbon dioxide accumulates and the climate warms again, melting releases materials stored on land and beneath glaciers. The oceans receive new pulses of phosphorus and iron. Microbial communities expand, collapse, and reorganize. Every environmental crisis filters the biosphere, favoring organisms able to survive unstable conditions. Oxygen also changes the minerals of the continents. Before its rise, many reduced metals can remain exposed without rapidly reacting. Afterward, weathering produces red beds, rust-coloured sediments formed when iron in rock combines with oxygen. Rivers carry oxidized material toward the sea. Sulfur chemistry changes. New mineral species appear because elements can now combine under conditions that did not previously exist. The surface becomes more chemically diverse, and the rocks begin preserving evidence of an atmosphere with a different character. A planet can therefore reveal the spread of invisible gas through colour. Red sediments on land and iron deposits beneath ancient seas record the slow advance of oxidation. In the upper atmosphere, oxygen molecules are broken apart by ultraviolet radiation. Some of the freed atoms combine with other oxygen molecules to form ozone. This gas gathers into a protective layer that absorbs much of the most damaging ultraviolet light. The shield is incomplete at first, and its strength follows the changing abundance of oxygen. Even so, the surface gradually becomes less exposed to lethal radiation. Life still remains mainly in water, where depth provides protection, but the chemical barrier above the planet begins preparing the land for a distant future. The significance is quiet. No forests yet rise, and no animals cross the shore. Yet a new atmospheric structure is forming through the activity of microscopic cells. The biosphere is altering the boundary between Earth and space. Within the ocean, oxygen opens a path toward greater cellular complexity. Energy is one of the central limits on life. Simple anaerobic metabolisms can sustain cells, but the efficient use of oxygen provides much larger returns from the same food. That advantage may later support cells with more genes, internal membranes, active transport, and complex structures. The first eukaryotic cells, containing nuclei and specialized internal components, emerge after long microbial evolution in a world where oxygen is becoming more available. Their origin involves a deep biological partnership. One cell takes another inside, but instead of digesting it, the two remain together. The internal cell becomes the ancestor of the mitochondrion, the structure that later allows eukaryotic cells to use oxygen efficiently. This union is not merely cooperation between two organisms. It creates a new kind of cell with an expanded energy supply and new evolutionary possibilities. The transition is still surrounded by uncertainty, and oxygen alone does not explain it, but the changing atmosphere provides an essential background. Even after eukaryotes appear, Earth does not immediately become a world of complex bodies. Oxygen remains far below modern levels for much of the following time. Deep waters stay anoxic or rich in sulfide, and nutrients are often trapped in chemical cycles that limit growth. The planet enters a prolonged middle age in which life diversifies slowly while the environment appears broadly stable. Yet the earlier revolution cannot be undone. Oxygen has entered the air, ozone has begun shielding the surface, and high-energy respiration exists. The old anaerobic world survives in sediments, marshes, deep basins, and within the bodies of later organisms, but it no longer defines the entire planet. The change also reshapes evolution through extinction. Organisms unable to escape oxygenated water lose territory, and some lineages vanish from environments they once dominated. Others survive only in hidden refuges where oxygen remains absent. Their descendants persist in mud, deep rock, stagnant water, and digestive systems, preserving ancient metabolic styles inside a transformed world. This survival shows that planetary revolutions are rarely complete. New chemistry spreads across the surface, but old worlds remain folded within it, protected in places the atmosphere cannot fully reach. The change begins with microbes releasing a gas they do not need. It continues through oceans that rust, climates that cool, rocks that redden, and cells that learn to turn poison into power. Earth's appearance remains stark, but its chemistry has crossed a threshold. The atmosphere is becoming a biological creation, and every breath taken by future life begins in these ancient sunlit waters. The planet now enters an interval so long and so quiet that it is often described as the boring billion. The name is misleading. Nothing on Earth truly stops. Continents continue to drift. Volcanoes release gases. Oceans circulate. Microbes compete. And cells experiment with new forms. Yet compared with the upheavals before and after it, the pattern changes only slowly. Oxygen remains present in the atmosphere, but at levels far below those of the modern world. The deep ocean is still largely anoxic, and in many places it is rich in dissolved iron or hydrogen sulfide. The continents gather and separate without producing an immediate transformation of life. Earth appears suspended between two revolutions, after the first great oxidation but long before animals, forests, and complex ecosystems. From a distance, the surface is still stark. Land is mostly bare rock, gravel, dust, salt, and volcanic ash. Along coasts and in shallow water, microbial mats form dark films over sediment. The open ocean contains microscopic life, but no schools of fish break the surface and no large bodies disturb the seafloor. The atmosphere carries more oxygen than before, yet not enough to support energetic animal life on a wide scale. The ozone layer offers greater protection from ultraviolet radiation, but the land remains almost empty because life has not yet developed the structures needed to resist drying, anchor itself, and draw nutrients from exposed stone. The world is habitable only within limits, most clearly revealed by the oceans. Near the surface, sunlight supports photosynthetic organisms, including cyanobacteria and early eukaryotic algae. Oxygen produced there dissolves into the upper water and may enter the atmosphere. Below this thin illuminated zone, oxygen is consumed by decay. Dead cells and organic particles sink from the surface, carrying carbon into darker water. Microbes feed on that material and use the available oxygen. Once it is gone, other organisms continue the decay through different chemical pathways. Some use sulfate and release hydrogen sulfide, the gas associated with the smell of rotten eggs. In enclosed basins and sluggish deep water, this process creates euxinic conditions, meaning water that is both oxygen-free and rich in sulfide. Such seas would be deadly to most modern animals, yet they support communities adapted to a chemistry inherited from the ancient Earth. The result is not a single uniform ocean, but a layered world. Oxygenated surface water lies above deeper zones that may be ferruginous, rich in dissolved iron, or euxinic, rich in sulfide. The boundaries shift with seasons, currents, nutrient supply, and the shape of ocean basins. Along these boundaries, microbes gather because useful chemicals meet there. One group releases a compound that another consumes. Energy passes from light to organic matter, from organic matter to oxygen-consuming cells, and then into sulfur, methane, iron, and nitrogen cycles deeper below. The quiet ocean is chemically divided into narrow habitats. This division helps explain why oxygen does not rise quickly. Photosynthesis continues, but much of the organic matter it creates is broken down before burial. The oxygen released in the surface is consumed again during decay, or by reactions with reduced minerals and volcanic gases. Only when organic carbon is buried without being oxidized can a lasting excess of oxygen remain. During the boring billion burial may be too limited and nutrient supply too low to drive a dramatic increase. Phosphorus is especially important because cells need it for membranes, genetic material, and energy transfer. Weathering carries phosphorus from land to sea, but ocean chemistry can trap it in sediments before it circulates widely. With much of the nutrient supply locked away, biological productivity remains constrained. A low oxygen world helps maintain nutrient scarcity, and nutrient scarcity helps maintain low oxygen. The system settles into a long feedback that resists rapid change. Continents contribute to the stability. Earlier in Earth history, intense volcanism and rapid crustal growth create large disturbances. During this middle interval, tectonic activity may become less extreme on a global scale. The supercontinent Columbia, also called Nuna, assembles and later begins to fragment. New oceans open, mountains rise, and sediment enters the sea. Yet these events unfold slowly enough that the average state of the planet remains broadly similar. Continental interiors expand, reducing the proportion of shallow coastal water where sunlight and nutrients can support high productivity. Long mountain chains weather away. Rivers continue delivering minerals to the sea, but without plants and deep soils. Erosion differs greatly from later times. Within the microbial world, evolution continues without leaving dramatic fossils. Eukaryotic cells diversify into several major lineages. They are larger than bacteria and contain nuclei, internal membranes, and mitochondria. Some also acquire chloroplasts through another ancient partnership. When a eukaryotic cell takes in a photosynthetic cyanobacterium and retains it, this event gives rise to algae capable of capturing sunlight within complex cells. Later, other eukaryotes acquire photosynthetic partners from these algae, spreading chloroplasts through additional branches of life. These unions transform biology, but the organisms remain microscopic or form simple filaments and colonies. Their innovations remain visually subtle. Sexual reproduction also develops among eukaryotes. Instead of producing only near copies, cells combine genetic material from different individuals. This reshuffling creates variation and allows populations to adapt more flexibly. The process is costly, but it becomes a defining feature of later eukaryotic life. During the long Middle Age, sex may help lineages survive changing local conditions even while the global environment appears stable. Predation may also begin at microscopic scales. Some cells engulf smaller cells and digest them internally. This creates new pressure in evolution. Prey develop protective walls, spines, larger size, or colonial growth, while predators become better at capture. An arms race begins without claws, teeth, or eyes. It unfolds among organisms invisible to the naked eye. Fossils from this interval are sparse, but they reveal hints of growing complexity. Some are simple spheres with layered walls. Others form long filaments, branching structures, or flattened bodies attached to the seafloor. Certain fossils preserve large, organized cells suggesting eukaryotic affinity. One striking later example is Bangiomorpha, a red alga whose fossils preserve multicellular filaments and structures interpreted by many researchers as evidence of sexual reproduction. Its exact age and evolutionary position remain subjects of study, yet it shows that complex cellular organization is no longer a distant possibility. Multicellularity begins to appear in different lineages, not as one invention, but as repeated experiments. Cells remain together after division, communicate chemically, and begin to specialize. Some anchor the organism, some gather light, and some take part in reproduction. Most of these experiments leave no descendants, but a few establish principles later used by plants, fungi, and animals. Climate during the boring billion may be comparatively stable, though not unchanging. The sun slowly brightens, while carbon dioxide, methane, clouds, weathering, and ocean circulation regulate surface temperature. Evidence for widespread glaciation is limited across much of the interval, suggesting that the planet avoids the severe global freezes of earlier and later times. Warm conditions may dominate, with little permanent polar ice. Without large ice sheets, deep ocean circulation is weaker than in the modern world, making it easier for lower waters to remain stagnant and oxygen poor. Tropical storms cross broad oceans, rain erodes barren land, and rivers carry sediment into shallow basins. The continents may be stained red, brown, grey, and black by iron minerals, volcanic rock, and microbial coatings. The sea may appear green in some regions because of dissolved iron and plankton, while sulfide-rich waters can support purple or green photosynthetic bacteria beneath the surface. What makes this interval seem boring is the absence of obvious milestones, but its slowness may be essential. Complex cells need time to refine internal machinery, regulate genes, cooperate, and compete. Ecological relationships develop gradually. Mitochondria become deeply integrated into host cells. Cytoskeletons support movement and changing shape. Membranes form compartments for specialized reactions. Genetic systems expand and become more controlled. None of these changes produces an immediate animal, yet together they build the cellular foundation from which animals can eventually arise. The long delay may reflect environmental limitation rather than biological hesitation. Complex cells exist, but low oxygen and scarce nutrients restrict their abundance and size. The ocean offers possibilities while keeping them confined. Earth therefore remains poised between capacity and opportunity. By the end of this long Middle Age, the planet is not the same world that entered it. The differences are subtle, distributed through cells, sediments, and chemical cycles. Continents have shifted. Eukaryotes have diversified. Photosynthesis has spread through new lineages. Sexual reproduction and predation have increased evolutionary pressure. Multicellular forms have appeared in quiet experiments. The atmosphere still holds limited oxygen, and the deep sea remains hostile. But the biosphere has become more capable than its surroundings reveal. Beneath the apparent stillness, the machinery of complexity is assembling. The boring billion is not an empty pause. It is a long preparation, hidden in water, waiting for the planet's chemistry to release what evolution has already begun. Rodinia does not rise from the ocean as a single act of creation. It forms through collisions that take hundreds of millions of years, as ancient continental blocks drift together across a planet already deep into its long Middle Age. Each fragment carries its own history of volcanic arcs, buried sea floor, eroded mountains, and older crust formed in worlds that no longer exist. When these fragments meet, the ocean between them narrows. Dense seafloor bends downward into the mantle. Volcanoes grow above the descending slab, and sediments are scraped, folded, and lifted. Eventually the water closes completely. Two continents press against one another, and the rocks between them are crushed into mountain belts that may rival the greatest ranges of the modern world. Around 1 billion years ago, enough of these collisions have occurred to assemble most of Earth's continental crust into a supercontinent known as Rodinia. Its exact shape remains uncertain because the later planet breaks it apart and scatters its pieces, leaving geologists to reconstruct the lost arrangement from matching rocks, magnetic traces, and the ages of ancient mountain belts. Yet the broad picture is clear. A vast concentration of land spans a great part of the globe, surrounded by an enormous ocean that occupies much of the opposite hemisphere. Rodinia is not the first supercontinent, and it will not be the last. It is one stage in a cycle driven by the motion of the mantle, a slow gathering and dispersal that reorganizes coastlines, climates, ocean currents, and the pathways available to life. The heart of Rodinia includes Laurentia, the ancient core of what later becomes much of North America. Other continental blocks press against its margins, including pieces that will one day belong to South America, Africa, Antarctica, Australia, and Asia. The names are modern conveniences applied to fragments that have not yet taken their familiar forms. At this time, there is no Atlantic Ocean, no Pacific in its modern shape, and no recognizable map. Land joins land in unfamiliar combinations. Mountain chains cross boundaries that later oceans will divide. Rocks now separated by thousands of miles may lie side by side, heated and deformed within the same collision zone. One of the largest of these events is the Grenville orogeny, a prolonged episode of mountain building that marks the assembly of Rodinia along the edge of Laurentia. The collision folds rock, drives it deep into the crust, and transforms it under intense pressure and heat. Magma rises through fractures and cools underground. Older minerals recrystallize into new forms. Sedimentary layers are squeezed, tilted, and carried upward. Across a broad belt, the crust thickens into a high plateau and a chain of mountains extending for immense distances. Much of that range later erodes away, but its roots survive in eastern North America and in matching terrains that are eventually carried to other continents. These deep rocks preserve the pressure of vanished peaks. They are the buried foundations of mountains that once stood beneath a sky with no birds, no trees, and no animals on land. From their slopes, rivers descend across barren ground. Without vegetation to hold the surface together, rain loosens fragments of stone and carries them rapidly toward inland basins and the sea. Sediment accumulates along the margins of Rodinia, while chemical weathering draws carbon dioxide from the atmosphere. The position of the supercontinent influences how much rain reaches its interior. Coastal regions may be wet and storm-beaten, while vast inland areas lie far from ocean moisture and become dry, dusty, and sharply seasonal. The land is enormous, yet almost entirely lifeless at the surface. Microbial films may survive in wet cracks, lake shores, and temporary pools, but there are no roots to deepen soil and no organic cover to soften the rock. Much of the continent is a hard expanse of exposed mineral, coloured red, brown, black, and pale grey under a dimmer sun. Rodinia also changes the ocean. With so much land gathered together, the total length and arrangement of continental margins are reduced. Shallow coastal seas, where sunlight and nutrients can support high biological productivity, become less widespread than they might be on a more fragmented planet. The great surrounding ocean stretches across a hemisphere with few barriers to redirect currents. Warm surface waters move over vast distances, while deeper layers remain poorly mixed and largely starved of oxygen. The geography of the supercontinent therefore helps preserve the chemical stagnation of the boring billion. Life continues in the sea, but the most productive habitats are unevenly distributed around the edges of a single immense landmass. Tectonic activity, however, never truly accepts stillness. Even as Rodinia reaches its greatest assembly, heat rises beneath it. Continental crust is thick and buoyant, and a supercontinent acts like an insulating cover over the mantle. Warm material gathers below, expanding and pressing upward. In some regions, the crust begins to dome and stretch. Faults open. Long valleys sink between raised shoulders of rock. Magma enters the fractures, cooling into dark sheets and broad underground intrusions. These are the first signs that the continent may not remain whole. Yet rifting does not always succeed. One of the most dramatic failed attempts cuts into the interior of Laurentia. The mid-continent rift begins as the crust is pulled apart across a line extending through what later becomes the centre of North America. The scale is enormous. Lava pours across the surface in repeated eruptions, filling basins with thick layers of basalt. Magma also cools underground, where minerals separate and fluids carry metals into cracks. Copper becomes concentrated within parts of this ancient volcanic system, creating deposits that much later human communities will find around the region of Lake Superior. The rift continues opening for millions of years and comes close to splitting Laurentia. Had it reached the edge of the continent and connected with the ocean, water might have flooded the valley and created a new sea. A large eastern portion of the land could have broken away, changing the shape of the future continent beyond recognition. But the rift fails. The pulling forces weaken or are redirected by the continuing collisions along Rodinia's margins. The crust stops separating, leaving a deep scar buried beneath younger rock. The wound remains visible only through geology, gravity measurements, volcanic remnants, and the Great Basin later occupied in part by Lake Superior. The failure reveals the tension within Rodinia. The same mantle forces that help gather continents can also begin tearing them apart. Collision and rifting occur almost together, not as opposites separated by neat stages, but as overlapping expressions of a restless interior. Along one margin, crust thickens under compression. Farther inland, it thins under extension. Mountains rise while valleys split open. Volcanoes erupt in both settings, though for different reasons. The supercontinent is therefore not a rigid lid. It is a shifting arrangement of blocks under continual stress. Its apparent unity conceals fractures that will later become oceans. Above this unstable foundation, climate and erosion slowly weaken the great mountain ranges. Rivers carry mineral grains into lakes and coastal basins. Freshly exposed rock releases phosphorus and other nutrients that can feed microbial communities. Isolated inland waters may escape some of the chemical restrictions of the global ocean, especially where seasonal cooling and river flow keep them mixed. These lakes become small worlds within the larger world, separated from the dark, deep sea and supplied by the mountains around them. Their significance is not yet visible from the scale of Rodinia, but they show how tectonic upheaval creates biological opportunity. A collision builds mountains. Mountains create rivers. Rivers feed lakes. Lakes offer conditions in which complex cells can experiment beyond the limits of the open ocean. Rodinia's importance therefore extends beyond the shape of the land. It controls the movement of water, nutrients, and heat across the planet. It influences where sediments are buried, where oxygen can accumulate, and where isolated habitats can persist. It helps maintain global stability even while preparing the conditions for future disruption. The supercontinent dominates the world, yet its reign contains the beginnings of its end. Beneath its barren interior, heat continues rising. Along its edges, old ocean basins have vanished, but new zones of weakness are forming. The mountains of assembly are already eroding into the sediments from which later continents will be built. The failed rifts prove that the crust can break, even if it has not yet broken completely. Rodinia appears permanent only because deep time moves too slowly for any single moment to reveal the full change. In reality, the supercontinent is a temporary gathering, held together by forces that never cease. Its rocks are pressed into unity while the mantle below quietly prepares their separation. Beyond the barren shores of Rodinia, the ocean stretches across the planet as a dark and chemically divided world. It may appear calm beneath the pale light of the younger sun, but the stillness hides a deep separation between water layers. Near the top, photosynthetic microbes gather where sunlight can reach. They release oxygen into the surrounding water, yet only a small amount survives. Dead cells and organic particles sink from the surface like marine snow. Microbes consume this material as it falls, using oxygen in the process. By the time the particles reach greater depths, the available oxygen is gone. Below that boundary, other forms of life take over, using chemical pathways that do not require it. The deep ocean becomes anoxic, and in many regions it also becomes rich in hydrogen sulfide. These conditions are known as euxemia, a state that combines the absence of oxygen with the presence of dissolved sulfide. To most modern animals, such water would be immediately hostile. There is nothing to breathe, and the sulfide interferes with the machinery of cells. Yet in this ancient ocean, organisms adapted to oxygen-free chemistry occupy the depths. The sea is not lifeless. It is organized by invisible boundaries, with each layer favoring a different metabolism. At the surface, cyanobacteria and algae use light. Beneath them, microbes consume organic matter, with the last traces of oxygen. Deeper still, sulfate-reducing bacteria release hydrogen sulfide as waste. Other organisms use methane, iron, or sulfur compounds, forming communities arranged according to the chemistry around them. The result is a water column divided into narrow ecological zones. A change of only a short distance can mean the difference between oxygenated water, sulfide-rich water, and water dominated by dissolved iron. These boundaries move with seasons, storms, currents, and the shape of the sea floor. They are not fixed walls, but shifting fronts where different chemical worlds meet. Along these fronts, life becomes especially active because substances produced in one zone become fuel in another. Yet this activity does not make the ocean hospitable to modern life. The deep sea remains stagnant over immense areas, with little or no permanent ice at the poles. There is less cold, dense water sinking to drive vigorous circulation. The great ocean surrounding Rodinia has few continental barriers to redirect currents and help mix the depths. Warm surface water can remain separated from colder lower layers for long periods. Oxygen from the atmosphere enters the upper sea but fails to penetrate far below. The lower ocean becomes isolated, preserving chemical conditions that would later survive only in enclosed basins such as the Black Sea. In the ancient world, however, these conditions may extend across vast regions of the global ocean. The darkness is not only the absence of sunlight, it is also a darkness of watercolour and suspended material. Dissolved iron can give some waters a greenish tone. Sulfur bacteria may add purple or reddish hues near the boundary where light and sulfide overlap. In the deepest basins, black mud gathers on the seafloor, rich in organic matter that decays slowly without oxygen. Fine particles settle through the water, carrying the remains of microbial life into sediment. The ooze traps chemical evidence of the ocean above, preserving traces of iron, sulfur, carbon, and the changing balance between them. No large creatures disturb these layers. There are no burrowing worms to churn the mud, and no scavengers to consume the falling material. Sediments can remain finely laminated, one thin layer resting above another, creating a quiet archive of an ocean that has no visible witnesses. The atmosphere above is also unfamiliar. Oxygen remains low, and greenhouse gases help keep the planet warm beneath a sun that is still dimmer than in later ages. Methane produced by microbes and carbon dioxide released by volcanoes both contribute to the climate. Nitrous compounds may add further warming. The exact mixture changes through time, but the general result is a warm world with limited permanent ice. Tropical storms draw energy from broad stretches of heated water. They travel across the open ocean with little land to weaken them, growing large before striking the coasts of Rodinia. Their winds churn the surface and may occasionally drag sulfide-rich water upward from below. When deep water reaches the air, hydrogen sulfide can escape as gas, carrying the odour of decay across the sea. Storm surges wash black sediment onto barren shores. Rain falls on rock without vegetation, sending pulses of nutrients into coastal water. The storms temporarily mix the upper ocean, but they cannot overturn the deepest basins on a planetary scale. Once the violence passes, the chemical layers form again. The ocean returns to its long stagnation. This state places severe limits on complex life. Eukaryotic cells need more energy and more nutrients than most bacteria. They require nitrogen and phosphorus to build membranes, genetic material, and internal machinery. In the open ocean, these nutrients are often scarce or trapped where they cannot be used efficiently. Phosphorus can bind to minerals and settle into sediment. Nitrogen changes form through microbial reactions and may become unavailable in the oxygen-poor water. Complex cells survive in the sunlit surface, along coasts, and near zones where rivers deliver fresh material, but they do not dominate the planet. Their world is patchy. A productive region can be separated from another by thousands of miles of nutrient-poor water. Even where oxygen exists near the surface, it may fall quickly below levels needed to support larger bodies. The ocean permits complexity without yet rewarding great size. The chemical boundaries also create danger for oxygen-producing organisms. If sulfide rises into the sunlit layer, it can poison many forms of photosynthesis. Yet certain bacteria thrive precisely in that overlap. They capture light without releasing oxygen and use hydrogen sulfide as a source of electrons. Their pigments absorb wavelengths that filter through the water, producing bands of purple, red, or green beneath the surface community. In some regions, the ocean may therefore contain a stacked spectrum of life, with oxygenic photosynthesizers above and anoxygenic forms below. Each group modifies the light and chemistry available to the next. The layered sea behaves like a living filter. Energy enters from the sun, passes through one community after another, and is finally lost into dark sediment. Methane rises from deeper zones and is consumed near chemical boundaries. Sulfide moves upward and reacts with metals or oxygen. Iron circulates between dissolved and solid forms. The ocean is constantly active, yet its overall structure remains trapped in balance. This balance helps explain why the atmosphere does not gain oxygen rapidly. Photosynthesis continues, but the organic matter it produces is mostly consumed. Oxygen reacts with reduced compounds from the deep ocean and with gases released by volcanoes. Only a small fraction of carbon is buried before it can be oxidized again. Without widespread burial, oxygen has difficulty accumulating. The ocean acts as a chemical buffer, absorbing the consequences of biological activity and keeping the planet in a prolonged middle state. Life pushes toward a more oxygenated world, while geology and decay pull it back. Neither side wins for hundreds of millions of years. Yet the apparent stability contains signs of future change. Along continental margins, Erosion delivers phosphorus from newly raised mountains. In isolated basins, water circulation differs from that of the open ocean. Freshwater lakes mix more easily because they are smaller, shallower, and influenced by seasonal cooling, river flow, and wind. Some become oxygenated from surface to bottom. Others receive abundant nutrients from bare rock. These local environments escape the harshest restrictions of the global sea. They form small chemical refuges where eukaryotes can grow more freely and experiment with multicellular organization. The contrast is profound. Across half the planet, the deep ocean remains dark, stagnant, and toxic to modern life. On scattered islands of fresh water, conditions resemble a distant preview of the future. The global ocean is therefore not simply a failed habitat. Its limitations create selection. Organisms adapt to narrow chemical zones, develop new metabolisms, and compete for scarce resources. Complex cells refine their machinery under pressure. Photosynthetic lineages diversify. Sexual reproduction increases genetic variation. Predation encourages defenses and larger size. The ocean's hostility slows expansion. But it does not stop innovation. It hides innovation in thin layers near the light, in coastal pockets, and in isolated waters beyond the influence of the deep sea. From the surface of space, Earth still appears empty of complex life. Beneath the clouds, however, the ocean is a layered machine, cycling sulfur, iron, carbon, methane, and nitrogen through communities older than any continent now recognizable. Its black depths preserve the chemistry of an ancient world, while its narrow illuminated margins hold the first hints of another. The planet remains divided between what life has been and what it may become. In that division, the dark ocean endures as both prison and laboratory, limiting the future while quietly helping to prepare it. High within the ancient mountains of Rodinia, far from the black depths of the global ocean, fresh water gathers in basins carved by faulting, erosion, and the slow settling of the crust. These lakes are small when measured against the surrounding sea, yet their isolation gives them a different chemical fate. Rivers enter from barren slopes, carrying dissolved minerals, phosphorus, nitrogen, and fine sediment weathered from newly exposed rock. Seasonal cooling allows surface water to sink. Wind pushes across the open basins. Streams flow in and out. Together, these movements keep the water mixed more effectively than in the immense stagnant ocean beyond the continent. Oxygen produced near the surface can reach deeper layers, while toxic sulfide is less able to accumulate. The lakes are not modern in every detail, but compared with the dark global sea, they are clear pockets of opportunity. Along their shores, microbial mats spread across wet sediment. Cyanobacteria form filaments beneath the light, while other microbes live below them in layers arranged by chemistry. Rain changes the water level. Dry intervals expose mudflats. Floods bring fresh nutrients from the mountains. Winter ice may cover the surface in higher or colder regions, then melt and overturn the water when warmth returns. These repeated changes prevent the lakes from settling into the long chemical stillness that defines much of the ocean. Life experiences stress, but it also receives renewal. Nutrients are stirred back into circulation. Oxygen reaches places that would otherwise become closed. Populations expand, contract, and adapt to conditions that shift from season to season. In one such ancient landscape, sediments later preserved in what becomes the western coast of Scotland hold evidence of a remarkable freshwater ecosystem. The rocks belong to the Rodinia sequence, a thick record of rivers and lakes that once lay within the eroding highlands of Rodinia. Today these rocks rise in austere cliffs and islands beside the North Atlantic, but around 1 billion years ago they formed the floors and margins of inland waters. Sand, mud, and mineral-rich runoff settled into the basins. In some places, phosphate became concentrated enough to preserve microscopic organisms with unusual clarity. Cells were trapped before decay erased their form, leaving tiny fossils sealed inside mineral matter. These remains reveal that the lake supported more than a thin coating of simple bacteria. They contained a varied community, including cyanobacterial filaments, small scavenging microbes, and larger cells surrounded by protective walls. Some fossils show shapes and internal organization consistent with eukaryotes, the complex cellular lineage that includes every later animal, plant, fungus, and alga. Their presence suggests that freshwater environments are not merely marginal shelters. They may be active centers of evolutionary experimentation. The open ocean favors organisms that can survive low nutrients, weak oxygenation, and chemically layered water. Inland lakes operate under different rules. Their catchments deliver phosphorus directly from rock. Their limited size allows faster mixing. Their shorelines create repeated wet and dry cycles. Each basin develops its own balance of temperature, salinity, acidity, and nutrient supply. Isolation separates populations from one another, allowing different traits to spread in different lakes. A lineage successful in one basin may never reach the next, while another evolves under contrasting conditions only a short distance away. This separation turns the continental interior into an archipelago of biological experiments. Not islands of land, but islands of water. Freshwater also presents challenges. Cells accustomed to the salty ocean must regulate water entering their membranes. Nutrient levels can rise quickly and then collapse. Lakes may shrink, overflow, freeze, or become cut off from their rivers. A population can flourish for thousands of generations and then vanish when the basin dries. Yet instability rewards flexibility. Organisms that alter their metabolism, form resistant walls, attach to surfaces, or produce dormant stages gain an advantage. Complex cells, with their internal compartments and larger genetic systems, may be especially capable of managing such change. They require more energy, but the better oxygenated water can help meet that demand. They need more phosphorus, but the surrounding mountains provide it. Conditions that restrict eukaryotes in the open sea become less severe within these inland refuges. Among the Rodinia fossils is a form known as bicellum. It appears as a tiny spherical body composed of more than one cell type. Rounded cells occupy the interior, while elongated cells form an outer layer. Different specimens preserve different proportions of these shapes, yet the overall body remains organized. This pattern suggests that the cells do not simply cluster by accident. They may change form, move relative to one another, and contribute to a coordinated structure. Bicellum is not confirmed as an animal, and its exact place in the tree of life remains uncertain. Still, it offers a glimpse of multicellularity becoming more than a chain or sheet of identical units. Cells may already be taking on separate roles within one body. Such organization is a crucial step toward complex organisms, because a multicellular body must solve problems that a single cell never faces. Its cells must remain connected, communicate, divide at controlled times, and preserve the shape of the whole. Some must gather energy, some must protect the surface, and some may eventually specialize in reproduction. Early experiments are likely simple and fragile, but the principles matter more than the size. A sphere smaller than a grain of sand can contain the beginning of cooperation between cell types. The lakes provide a setting where such cooperation may be tested repeatedly. In oxygenated water, larger bodies can obtain more energy. In nutrient-rich shallows, growth is less restricted. On lake bottoms and submerged surfaces, colonies can attach without being carried into the open ocean. Predators, if present among larger single-celled eukaryotes, create pressure for cells to remain together after division. A cluster may be too large to engulf. An outer layer may protect the cells within. At the same time, cooperation creates new vulnerabilities. A body depends on its cells behaving as parts of a whole, rather than reproducing only for themselves. Mechanisms that control growth and eliminate damaged cells become increasingly important. The deep biological problems later solved by animals may begin in modest forms within these quiet waters. Other lakes elsewhere on Rodinia likely support different communities. Some are alkaline, some acidic, some clear, and some cloudy with sediment. Volcanic regions add sulfur and metals. Mountain basins receive cold runoff. Lowland lakes warm beneath strong sunlight and may shrink during dry seasons. No single refuge represents the whole freshwater world. Their value lies in diversity. The global ocean imposes one broad chemical structure over enormous distances, while isolated lakes multiply environments. Evolution gains more boundaries, more gradients, and more chances for populations to diverge. The continent, though barren above the waterline, begins to influence life through the basins it holds. Rivers connect rock to biology. Erosion feeds cells. Seasonal weather creates cycles of disturbance and recovery. Even the failed rifts and ancient mountain collisions of Rodinia contribute by producing depressions where water can remain. Their fossil record is rare because freshwater sediments are easily eroded or altered, making each preserved basin unusually valuable. What survives is therefore only a narrow window into a much larger hidden landscape. Countless lakes leave no readable trace, yet they may have hosted similar experiments, allowing complex cells to spread between rivers, temporary pools, and enduring inland seas. These freshwater ecosystems do not immediately transform the planet. Their inhabitants are microscopic, and many lineages disappear without descendants. The atmosphere still contains little oxygen. The open ocean remains divided and hostile. Land remains exposed to ultraviolet radiation and severe drying. Yet the lakes demonstrate that Earth is no longer governed by one global limitation. Local environments can escape the chemistry of the wider world. Within them, complex cells can become abundant. Multicellular forms can organize, and evolutionary experiments can proceed at a faster pace. The most important changes may therefore occur not in the largest habitat, but in small protected systems scattered across the supercontinent. From the shore, a Rodinian lake would seem silent. Wind moves over the water. Sediment clouds the shallows after rain. Snow may remain on distant peaks. No animal breaks the surface, and no plant rises along the bank. Yet beneath the calm, cells divide, attach, compete, and cooperate. Some form filaments, some build walls, some gather into bodies with an inside and an outside. The global ocean still holds Earth in its long chemical stasis, but these inland waters reveal a way around it. In small basins fed by stone and stirred by seasons, the future is beginning to take shape. There is no sudden dawn in which the ancient oceans fill with animals, and no single fossil marks the instant when simple cells become the ancestors of larger bodies. The transition unfolds through countless experiments, most of them microscopic, scattered across shallow seas, coastal pools, and freshwater lakes. By around 1 billion years ago, eukaryotic cells are already established. They contain nuclei, internal membranes, mitochondria, and a level of organization far beyond that of bacteria and archaea. Their complexity gives them possibilities, but it also creates demands. They need more energy, more phosphorus, more nitrogen, and more reliable access to oxygen. In the dark, stratified ocean, those resources are limited. near sunlit coasts and within well-mixed lakes. However, the restrictions loosen. Here, larger cells can grow, exchange genetic material, and remain connected after division. The future begins not through size alone, but through cooperation. A single eukaryotic cell can change shape, engulf food, sense its surroundings, and control many internal processes. When several such cells remain together, new problems appear. They must communicate. They must coordinate growth. They must prevent the group from breaking apart whenever one cell divides. They must allow nutrients to reach the interior and remove waste from cells no longer touching the surrounding water. These challenges are severe, yet each solution creates a new level of possibility. A cluster can become too large for a predator to swallow. A filament can reach toward light while remaining anchored below. An outer layer can protect inner cells. Some cells can specialize in feeding, others in attachment, and others in reproduction. The body becomes more than a crowd when its parts begin serving different roles. Fossils such as Bangiomorpha preserve one expression of this change. Its cells form filaments attached to a surface, growing upward into the light. Near the tips, structures appear that resemble reproductive regions in later red algae. The interpretation remains cautious, but the organization suggests a multicellular eukaryote with a controlled life cycle. More importantly, it may preserve evidence of sexual reproduction. Sex changes evolution by combining genetic material from different individuals. Simple cloning produces descendants that are nearly identical except for mutation. Sexual reproduction reshuffles inherited variation in every generation. Harmful combinations can be removed. Useful combinations can appear, and populations can respond more quickly to changing conditions. The process is inefficient in some respects, yet it gives complex life a powerful method of experimentation. Every generation becomes a new arrangement of ancient genes. In a stable world, that flexibility may seem unnecessary. Yet the boring billion is stable only at the larger scale. Local environments change constantly. Lakes dry and refill. Shorelines shift. Nutrient levels rise after storms and fall during calm intervals. Oxygen expands through surface water and retreats when decay consumes it. Predators appear within microbial communities. Viruses move genetic material and destroy vulnerable cells. Sexual reproduction gives eukaryotes a way to keep pace with these pressures. It also allows separate cell types to evolve within the same organism through controlled differences in gene activity. Every cell may contain nearly the same genetic instructions, yet one part of a body can use those instructions differently from another. This separation between shared information and specialized function becomes essential to later multicellular life. Bicellum offers a different glimpse of the transition. Its tiny spherical bodies contain rounded inner cells and elongated cells around the outside. The fossils do not reveal movement, feeding, or ancestry with certainty, but they show an organized arrangement that is difficult to explain as a random cluster. The outer cells may protect the interior, help the group move, or control contact with the environment. The inner cells may serve another role. Even if Bicellum lies far from the direct ancestry of animals, it demonstrates that cells are already exploring division of labor. Cooperation also requires restraint. A cell that reproduces without regard for the group can consume resources and disrupt the body. So early multicellular organisms need mechanisms that control division and remove damaged or disobedient cells. Modern organisms solve this through networks of genes, chemical signals, and programmed cell death. The earliest versions are likely far simpler, but the evolutionary problem is already present. Selection begins acting at more than one level, favoring both successful cells and successful groups of cells. A stable body must reproduce as a whole, pass its organization to descendants, and preserve cooperation through repeated generations. This may encourage life cycles that alternate between single cells and multicellular stages. A solitary stage can disperse, while a collective stage can feed, grow, or resist predators. Once such cycles become reliable, complexity is no longer an accidental cluster. It becomes inherited architecture. Multicellularity is not invented once. It arises repeatedly among algae, fungi, and other eukaryotic lineages because cooperation offers recurring advantages. Many early attempts remain simple. Some form sheets, some branches, some hollow spheres, and some irregular colonies. Most leave no fossil record, yet each experiment tests the rules of adhesion, communication, growth, and reproduction. Predation may accelerate this process. A larger single-celled organism can engulf smaller cells whole, turning the microbial world into an arena of pursuit and defense. Prey respond by building thicker walls, growing spines, increasing in size, or remaining attached after division. A colony too large to swallow gains immediate protection. Once cells stay together for defense, natural selection can refine the association for feeding, movement, and reproduction. Predators also benefit from greater size and improved sensing. An evolutionary contest develops in water that appears empty to the unaided eye. There are no teeth or claws, but there are membranes, chemical signals, sticky surfaces, and flexible bodies. The pressure to capture and avoid capture begins shaping complexity long before animals become visible. Oxygen remains a central limit. Mitochondria allow eukaryotes to extract large amounts of energy from food when oxygen is available, but much of the ocean still lacks it. Complex communities therefore gather where oxygen production, circulation, and nutrient delivery overlap. Shallow shelves, river mouths, tidal flats, and freshwater basins become favoured zones. The geography of Rodinia creates both restriction and opportunity. Its vast interior reduces widespread coastal habitat, yet its mountains, rifts, and lakes generate isolated refuges. As the supercontinent begins to weaken, cracks open through the crust and new coastlines slowly form. Weathering attacks fresh rock, carrying phosphorus toward the sea. Ocean circulation begins to change. These tectonic shifts do not immediately end the long stasis, but they disturb the balance that maintains it. More nutrients can support more photosynthesis. Greater burial of organic carbon can leave more oxygen behind. Rising oxygen can alter ocean chemistry and expand the territory available to energetic life. The system is approaching instability. The coming transformation will not be gentle. Rodinia will break apart. Climate will swing toward extreme glaciations, and ice may spread across much of the planet. Oceans will reorganize, nutrients will be trapped and released, and oxygen levels will change unevenly. Many lineages will vanish, while others survive in open water, beneath ice, around vents, and within small refuges. The world that emerges from those crises will support organisms larger and stranger than anything yet present. But the foundations of that future are already here. They exist in the nucleus that controls a complex genome, in the mitochondrion that provides energy, in the chloroplast that captures light, in the sexual cycle that reshuffles inheritance, and in the adhesive molecules that keep daughter cells together. They exist in the first bodies with an inside and an outside, in the first cells that sacrifice complete independence for the success of a group, and in the first ecological contest that rewards size, coordination, and specialization. Earth still looks alien. The continents are bare, the sky carries little oxygen, and the deep ocean remains black and sulfide-rich. Yet the planet is no longer waiting for complexity to begin. Complexity has begun, and is waiting for the planet to permit its expansion. The difference is profound. Earlier Earth lacks the biological machinery for animals, plants, and fungi. This Earth possesses much of that machinery in scattered, modest forms. What remains is a change in scale, ecology, and opportunity. In quiet lakes and illuminated shallows, cells continue dividing. Some separate and live alone. Others remain together. Among those fragile unions lie the beginnings of bodies, ecosystems, and the visible living world. The long stillness is nearing its end, not because life suddenly appears, but because life has spent immense time preparing for a world that is about to change.